All right, welcome to the second part of page 2. This one's going to take a little bit of time, so there's kind of like space on page 2 and page 3 to get this completed. And so that's why I went ahead and changed up these videos, just broke them up a little bit different. So if the force that acts on a particle is known, then the acceleration can be found from Newton's second law of motion. So the vector version of this law states that if at any time t a force, so in this case vector force, acts on an object of mass m producing an acceleration a of t, then the force vector is equal to the mass times the acceleration vector, all those at time t. So we're just going to use this formula to help us determine just some parts of certain types of situations. So we're going to start with example 3. So this comes from 23 in the textbook, but a projectile is fired with an initial speed of 200 meters per second and angle of elevation is 60 degrees. We want to find the range of the projectile, the maximum height reached, and the speed at impact. So the first thing that we're given the initial speed. So because we're given initial speed, we can say the magnitude of the velocity vector at 0 is going to be 200 meters per second. Now, the angle of elevation is 60 degrees. Right, angle of elevation is 60 degrees. All right, so if our angle of elevation is 60 degrees, if we do a unit vector in the direction of velocity, all right, we can say if we're going 60 degrees, and we want to do a unit vector, we're basically going to use the unit circle, but we have 60 degrees there. So we could say, well, for x, it's cosine 60 degrees I plus sine, so this is our y, sine of 60 degrees j, and that's equal to, well, cosine of 60, we know that's going to be 1/2, so 1/2 I plus sine of 60 is square root of 3/2 j. All right, and so now what we do is we have, a velocity function, but we know, and let me go ahead and say that's v of t. Well, it's not necessarily known exactly that's v of t, so we'll just write, that's going to be our velocity vector. And we're going to say that because we have v of 0, and we know that that's going to be, if we have our unit, this is our unit velocity vector, and we're starting off at 0, we're going, a speed of 200, we can multiply our unit velocity vector by 200. So 1/2 I plus square root of 3/2 j. So again, this is our unit velocity, and we know how fast we're going at 0, so that's going to be a speed of 200. So then we could set up, our v of t for this equation, all right, is going to be 100 I plus 100 square root of 3 j. All right, and if we're setting this up where our projectile starts at the origin, then our r of 0 is equal to 0. So we're starting at the origin of this projectile of, an xy plane. We're going to start at the origin. All right, so that's why our r of 0 is 0. So our position is the 0 vector, and I'll note it by that. All right, so that's our starting, position. We're starting at the origin, so the origin vector. So what this formula is going to allow us to do, it's going to allow us to help us find, our acceleration. So if we ignore air resistance, the only force that is going to act upon our projectile is going to be that of gravity. And so if we have our force, that's going to be equal to our mass times our acceleration vector. And then that's just going to be negative m times the pull of gravity. All right, and so what do we know our pull of gravity? And then make sure we put our vector j there. So our pull of gravity, if we're doing the pull of gravity, that's going to be G is equivalent to 9.8 meters per second squared. Again, the reason why we're doing meters per second is because that's what our initial velocity is. So that's why we're using 9.8. So then that means that our A of t is just equal to negative 9.8 j. All right, and again, the only reason why we're doing vector j here is because if this is the acceleration vector, when you do the acceleration, and since it's of two components, and the only the only force acting against our projectile is gravity. That's why it's only in terms of j, because that's the only force. So we have A of t is equal to negative 9.8 j. And if we integrate that, what we do have is we can find our v of t. So if I integrate to A of t to both sides, I'm going to have v of t. And that's going to equal negative 9.8 t, not negative 9.8, well, negative 9.8 t j plus c, whatever our constant is. But we do have an initial velocity, and that initial velocity, what we can say is, oh, if I already have a c, let's put it right here, c is just our initial velocity, and we do have an initial velocity function, and our initial velocity vector is 100 I plus 100 square root of 3 j. So because I already have that initial velocity vector, I can go ahead and add the two. And so then I can say v of t, the vector function, is equal to, I'm going to go ahead and put my 100 I plus, and then I'm going to combine my j component. So 100 square root of 3 minus 9.8 t j. All right. So now I have a velocity function. Well, from this velocity function, I can get my position function. And so my position is going to be just the integral of the velocity function. So I'm going to integrate again. So I'm going to integrate to both sides, and I'm going to have r of t is equal to 100 t j, I plus 100 square root of 3 t minus 9.8 t. So I'm going to have 9.8 divided by 2, which is going to be 4.9 t squared j. And then plus, instead of saying, another constant c, I'm going to say, or another, not constant, but another, vector c, I'm going to add another vector. And that, I should have said vector c, vector d. And so do I have an initial position? All right, well, we know that d, let me get back to, we know that d is just equal to our initial vector, which is the 0 vector. So therefore, our r of t our position vector is 100 t j plus 100 square root of 3 t minus 4.9 t squared j. And then there's our position vector. So the only thing that we really used Newton's second law of motion was to help us find the acceleration. All right, so right here is where we use Newton's second law of motion. All right, now there's a few questions that was asked. So the first one is A, and so A is find the range of the projectile. And so let's go ahead and do A right here. So we're going to find the range, and so finding the range, we want to pretty much determine, how far our y value is going to go. So we want to find out when our projectile reaches the ground. So let's go ahead and write our parametric equation. So x of t is just 100t, and y of t is equal to 100 square root of 3 t minus 4.9 t squared. So we want to find out when the projectile reaches the ground. So we want to find out when y of t is equal to 0 and when t is greater than 0. All right, so we just can't forget that. We can't go back in time. So what we're going to do is we're just going to use our calculator and do 100 square root of 3 t minus 4.9 t squared. We want to find out when that actually equals 0. And so one thing that we can do is, well, this isn't bad because we can say, oh, hey, I can pull out a t and I get 100 square root of 3 minus 4.9 t. Is that equal to 0? So I have t is equal to 0 at t is equal to 0, and subtract 100 square root of 3, divide by negative 4.9, so t is equal to 100 square root of 3 over 4.9, which using your calculator is going to give you 35. .3. So that's when, because the 35.3 seconds is when it's going to reach the ground. So the range is going to be, how far is our missile, traveling. So if we want to go ahead and plug in when, so to find out how far on the x-axis, so y tells us, when we're going to approach 0, so when we're going to hit it. So what's the range, how far this missile is going to travel? It's going to be x of 100 square root of 3 over 4.9. And so I'll go ahead and plug that into my formula. 100 times 100 square root of 3 over 4.9, and that's going to give me an approximation of 35 meters. So that's how far the missile's traveling. All right. Now, if you recall from Calc 1 to find the maximum height, that's when you're going to have a critical number for your y of t. And so what we want to do, in order to find critical numbers, what did we do? We took the derivative of our, y, and because we wanted to find, when is that going from positive to negative, so when is that 0? And so when we want to find where the derivative is equal to 0. So let's go ahead and take the derivative of our y of t. So y prime of t is equal to just 100 square root of 3 minus 9.8 t. And what we want to do is we want to find where that's going to equal 0. So setting that equal to 0, 100 square root of 3 minus 9.8 t equal to 0 gives us a time of 100 square root of 3 divided by 9.8. So that is when. So 17.7 seconds. So that is when. So the maximum height is going to occur when our time is 17.7 seconds long. So to find out how high we traveled, we're going to do y of 100 square root of 3 over 9.8. And that's equal to just we're going to plug that into our y of t. So plugging that into y of t gives us 100 square root of 3 times 100 square root of 3 over 9.8 minus 4.9 over 100 square root of 3 over 9.8 squared. All right. When we plug that in, use a calculator, you're going to get 1,531 meters. All right. Last part, C, and I know there's other ways to do this because I know a bunch of you are taking physics, so you know a different way to do this. I'm just showing you how we can apply the calculus that we just learned to help solve this. All right. So the last question was the speed at impact. So what we want to determine is, how fast our projectile was traveling when we actually impacted. And so we know when we impact. Impact was 35.3 seconds, or 100 square roots of 3 over 4.9. All right? And we know that our velocity is going to tell us when, how fast we're traveling at impact. So we're going to do the velocity of 100 square roots of 3 over 4.9. And we're going to plug that into our velocity vector function. And let's see what that was again. So we have 100 plus 100 minus 9.8. So 100 I plus 100 square root of 3 minus 9.8. Now times our actual time, which is just 100 square root of 3 over 4.9 J. And it looks like what we're going to get is 100 I plus 9.8 divided by 4.9 is just 2. So minus 2 is 100 square root of 3. So minus, let me go ahead and change that so minus 100 square roots of 3 J. All right, and so now that's our vector at impact, and so the speed is just going to be the absolute value of that. I mean, the magnitude of that. So V 100 square roots of 3 over 4.9. And so we're going to get the square root of 100 squared, 10,000 plus 30,000. Made that a little too long, but that's okay. I have room. So 200 meters per second. All right, and I'm going to highlight all the answers, and then we are finished. Again, I would ask, are there any questions about this? But again, ask questions when you have them during class.